My name is Michael Heyeck. I'm the cloud architect here at Nebulon. And I'll say a little bit about my background because I think I'm one of the few people here who does not come from a storage background. Before I was at Nebulon, I was at Snap. While I was at Snap, I worked on their operational metrics team, which turns out to be very relevant to what we do here. And I also ran their stories back end for 4 years. Whether or not I got an offer to join because someone confused the word stories with storage, I will let you decide, but that's where I came from. Now, Josh talked about Nebulon ON and how it connects, how it tells the SPUs what to do. To kind of reiterate what it is, it's the connective tissue between all the hardware that the customers bought and their back-end administrative processes for IT. It provides monitoring and administration functions. Obvious question is, why did we build it in the cloud? And to talk about that, we need to talk about the traditional storage operating system. Traditional storage operating system's got two parts. The first is the IO stack, and the second is the management stack. And these are very different pieces of software. The IO stack is an extremely performant, highly optimized, and in no way implying that it's simple, but works with a fairly strictly defined set of interfaces. That what the IO stack is supposed to do doesn't change very much over time. The management stack, on the other hand, is human-facing, and it tends to be a lot more idiosyncratic. It tends to change a lot more with conventions or UI practices or customer feedback. And these two pieces of software, as I said, do not live well together. The IO stack is the heart of the system. It's the most important thing. Without that, the storage solution has no value. As a result of this, the vendor is going to be extremely cautious about releasing new firmware images. And customers are going to be reluctant to install new firmware images because why change something that's working? What this means over time is that your management stack is going to be likely very far behind what the state of the art is and what's the latest that's available. And if you're running a large installation, your management stack is going to be fragmented as different pieces of hardware are running different versions of firmware. By splitting these two things up and putting the management stack in the cloud, we get significant benefits for both. For the IO stack, the primary impact is that the firmware is now much smaller. It's much smaller, it's much simpler, and it's going to need much fewer updates, many fewer updates. And when an update does happen, it's going to be easier to administer because the control plane is still running in the cloud and not changing, and only the firmware on the individual cards is changing. For the management side, this allows us to update the management at a much higher rate, where we can release features not in months or maybe a year, but we can release a new feature in hours. And when we do release a new feature, it's available across the entire organization. All the hardware the customer has will benefit from the new administration interface. And this is a theme that I'll return to, we can continually add new backend implementations. In particular, as we collect more data, as new AI techniques become available, we can get better and better about predicting faults and recommending courses of actions to the customer, all without the customer needing to change anything on their system at all. Now, I have enormous respect for the hardware guys. I'm really blown away by what they do and all that physics they have to deal with. But when it comes time to talk about what you've built, they do have one advantage in that they have the cool device that they can show. And I have nothing to show you. Nebulon ON is made up of CI/CD pipelines and microservices and orchestration frameworks and persistence layers, and it's all very vague. So I'm going to talk about a couple of the design principles we used to try to deliver software as quickly as possible and with as high quality as possible. The first is the general notion that you want to use the right tool for the job, which sounds unexceptional. And by this, I mean, in the short term, we have different persistence layers. We have an RDBMS persistence layer, and we have a NoSQL store, and we have bulk storage because we have different kinds of data. And a user table is not the same thing as an audit log, which is not the same thing as logs from the SPU that we're storing in bulk. These are just different problems, use different tools. But the more interesting thing is that being in the cloud, new tools are available all the time. Tools change and practices change. And therefore, we spent a lot of time, wherever possible, making the choice to use agnostic interfaces, well-proven interfaces that let us change out the backend implementations that we're relying on. For instance, of course, we're using RDBMSs, we're using SQL. That's a very long-standing, very stable standard. We can change from, to be a little transparent, we're using a cloud provider, RDBMS at the moment. It's trivial for us to change to a different cloud provider because they all speak the same dialect. For metrics, which we'll talk about in a bit, we standardize on Prometheus and the PromQL EDM, which is very popular, supported by a lot of TSDBs. Where there was no standard, we built our own abstraction layers. We did this for bulk storage, and we did this for our NoSQL stores in order to be able to switch, again, between vendors and between technologies as they change over time. On the executable front, we did commit to containers, which seems like a good bet. Right now we're using Kubernetes as an orchestration framework, but if in 3 or 4 years something else is different, we can switch to that easily enough. A concrete example of one of the technologies we're using, I'll talk about our TSDB. When I was doing observability and application metrics before, we had a lot of metrics coming into the system, and we had a lot of time series, but we were mostly interested in aggregated data. If you're looking at your API call rates and error rates across your system, you tend not to be interested in what any one system any one server is doing. So you can roll up your metrics and you end up with tens or hundreds of millions of time series. In an Internet of Things application, like what we're doing here, you can't do aggregation. Every SPU, every volume has metrics that are unique and interesting in itself. And this means we need to pick a TSDB with really huge scale. We picked M3DB, which comes out of Uber, which also has an obvious IoT problem with drivers and cars and whatnot. We picked that for 2 reasons. First of all, it seemed like a good technology. Secondly, because it talked Prometheus. And that means that if we decide to switch to another technology, I don't know, timescale, something like that in the future, we can do that, again, easily without changing any of our application code. The other design principle I'll talk about is an API-first approach. This means different things to different people. What it means to us is that there are no secret APIs. Everything that our system does, everything that the UI does, it does through published, documented, publicly available APIs. And we'll talk about this a bit more, but this means that a customer who wants to automate can avoid our UI, avoid our system entirely, and talk directly to our API. The other part of API first was that where we had a choice to make between optimizing a particular function and elegance and orthogonality, we went for elegance and orthogonality. This makes the API easier to maintain, easier to iterate on, easier to test, and easier to release quickly. Now, the question about the cloud, having talked about the benefits it gives, is obviously going to be, is it available and is it secure? There are 2 answers to the availability question. The first is the simple stuff. You can deploy, and we do deploy to multiple AZs, so that if misfortune happens, as it does, and an AZ goes down, the cloud infrastructure that we built will continue to run without interruption. However, bad things happen. Floods happen, fires happen, the world is full of backhoes, and I once worked with a guy who spent an interesting afternoon reading about fire suppression best practices for diesel generators as a result of a postmortem that we were doing with the cloud provider. So we've built the SPUs to continue to function even if cloud connectivity is totally lost. If the network's cut, you can't get to the cloud, the SPUs will continue to do reads and writes and mirrors and failovers without interruption until the cloud comes back. On the security front, again, there are simple things and there are complicated things. Simple things are, for instance, role-based access control. We have a system that allows an administrator to create users. Yes?
Can I ask a question about that last
Sure thing.
So if you lose access to the cloud, SPUs keep on going. I kind of get that. As far as all the data that you're sending back up to your cloud management, is that being stored locally? Is there a limit to that that you have? I mean, how long can the cloud be out before you start losing some data? Not but management.
We've designed for a 12-hour outage. Now, in that time, depending on the volume of metrics we're sending back, that could overflow the buffers. So you might have some TSDB gaps when the cloud comes back, depending on the outage and depending how many metrics are configured to send back.
Okay, and how large is that data? So if you guys tested that, been an outage of maybe 6 hours, is that sizable, or is it kind of pretty reasonable amount of data you have to send up back to your cloud?
I would have to defer an answer to that because the answer is it changes. It depends, for instance, how many volumes you have, how the system's configured, and it depends how aggressively we've configured the telemetry data to come back. Okay. So I couldn't give you a concise answer, unfortunately. Okay, role-based access control. We can set up an administrator can set up users, can grant very narrow permissions to those users so that administration of the system can be delegated. Also, Josh spoke about data being encrypted, the actual data that's being stored being encrypted. Of course, all the management data as it flows between the user and the cloud and the SPUs is encrypted in transit. And of course, it's encrypted at rest. So all the administration data is encrypted at rest on the cloud. The more interesting thing is the security triangle. With the cloud management solution, of course, a user is going to ask, suppose a bad actor gets control of the cloud. There's plenty of news stories you can look at. I think, well, I'm not going to name names, but there's in the news some unpleasantness recently. To mitigate this, to prevent this from happening, we've created the security triangle. So let me walk you through how a user would actually make a change to the system. First, the user logs into the cloud, presents their credentials, and sends up a request saying, I want to add a volume to SPU A. Cloud looks at the user's credentials, looks at the user's permissions, and says, okay, you're authorized to make this change. Cloud creates a token, cryptographically signs it, says, at such and such a date, user was authorized to make this change, and returns that token to the user's browser, or the user's agent, I should say, because it could be an agent the user wrote themselves. It could be one of our SDKs. The agent then forwards that token to the affected SPU. So it'll talk over the data center network to the actual SPU A that's being modified. The SPU will take that token, sign it, saying it's such and such a date. This token passed through my processing, send it back to the cloud. The cloud then checks both the signatures, sees that it's a valid operation, and creates recipes that the SPU can execute. Now, there's a minor technical detail here. The cloud does not actually send recipes to the SPU because the SPU is behind a firewall. It may not be reachable. It just essentially puts the recipes in an inbox that the SPU pulls. Sometime later, the SPU pulls down those recipes. It checks their associated token and says, okay, this recipe matches this token. This token was signed by the cloud and it was signed by me. That means I'm being instructed to make this change by someone who the cloud said is authorized, and I say had network access to me. And then it'll go and make the changes. What this means is that you cannot make a change to an SPU unless you have network access to it. This is the same level of, same limitation that you would have if you were making changes on a local management console. Now, this is obviously a little complicated. You have to get tokens and forward them, and there's a fair amount of mechanics to this. And as I said before, we've optimized the API to be orthogonal rather than adding syntactic sugar for particular use cases. To make this easier for the user, which is very important to us, we provide a number of SDKs, Python, C#, PowerShell, and we've got infrastructure as code integrations coming for Ansible, Terraform, and so on. This smooths out some of those difficulties that come from those 2 points I mentioned. The reason we want to make the SDK and the API easy to use is that fleet management is an important part of our story. If you want to manage a large fleet, if you've got 1,000 SPUs and 24,000 drives, and you want to do a firmware update across that, the last thing a customer is going to want to do is go to each individual SPU and start running jobs. By using the SDK and what I'll glibly refer to as a little scripting, a user can talk to our endpoint and drive a firmware update across their entire fleet. Similarly, across the entire fleet, a user can control boot drives or golden images. The other side to management is observability. And we have, I'd say, two kinds of observability. We've got what we call config data, which is the ability to look at all the SPUs in your organization and sort them by data center or sort them by application or look at all the SPUs in a particular lab. And then we also have time series data where we make IOPS and capacity information available so you can look at it side by side with application data that you get from other domains. Of course, the goal is not really to have customers digging through the UI, looking for individual SPUs, or putting graphs side by side in Grafana, trying to figure out what went on. We want to proactively tell the customer what goes on. So we, of course, monitor the system, and we can raise alerts. We can raise alerts on hardware failures or predicted capacity exhaustion, this kind of thing. But one of the nice things about having our management and our observability in the same interface, in the same place in the cloud, is we can produce actionable alerts, where we can say not just, we think you should change the configuration of this npod, but we can say, we think you should change this configuration of the npod, and here's a button that will do that if you click it. This is the same experience that you get from a cloud provider. And again, it's about getting this one touch, very smooth workflow for the end user. Now, the next step beyond simple things is, of course, ML and AI. And I think we all know how powerful these techniques can be. I will claim that an important input to high quality ML and AI is high quality data. And one of the nice things about our system is we have a lot of context for what the npods are doing. A traditional storage appliance is fine, but it has to deal with a very heterogeneous load. It doesn't really know whether it's getting, it doesn't easily know, I should say, whether it's getting requests from a database or a VMware workload or Kubernetes. It has to work a lot harder to have context for what it's seeing. On the npods, we have that context. So this lets us have much higher quality data. And this lets us do a number of AI related things and to add more over time. I'll talk about three kind of applications that AI can be used in. The first is simply ticket routing. That if a user has a problem and creates a ticket, we can look at what was going on in the system at that time, apply a little machine learning, and route that ticket more efficiently to our support staff to get a faster response to the customer. The second level is when a user creates a ticket, we might be able to suggest automatically suggest a resolution to it, where based upon the logs and the metrics and what we've seen in the past, we might be able to say, here's a knowledge base article, here's a proposed remediation for what you're seeing. And of course, the third interesting thing is prediction, where we can say, where we're looking not just at what the logs and metrics were during an event, but we can look at what the logs and metrics were before an event. And when we see those patterns reoccur, we can again create a proactive actionable ticket saying, we think you should change your configuration. We think your mirroring is not optimal for the workloads you're running. Here's a button that you should click to change that. Continuing with the theme of helpful buttons.
So from a question perspective,
Sure.
The host is looking at the SPU as if it's a SAS drive. Is that what it looks like?
I believe that's correct. Again, I don't have a storage background, but yeah, I would say it looks like a controller card.
And you're saying you've got more application data coming, context information, you called it?
Yes.
And how's that available to the SPU and then onto Nebulon ON?
Well, kind of what I was going to talk about here is that when an npod is created, it can be created with a particular workload. We can create a particular template, I should say. So if we create an npod, we know it's a Kubernetes npod, for instance. And so therefore we know what kind of workload it's running, and based upon what Kubernetes does, we have more context for the kinds of operations it's going to be issuing. If someone creates a template for MongoDB, then we know a lot about MongoDB and we know how MongoDB interacts with our system.
But there's a little more to it. There are application agents built into the SPU. So when the customer configures the pod to run, say, VMware, they can actually configure at the time they're creating the pod, the IP address of vSphere and the credentials for vSphere. That credential, it has to be only read-only. Then it gets configured in the SPU, and the agent inside the SPU interrogates vSphere and sends the metadata related to the vSphere environment back into the cloud. So now you have an end-to-end view of what's going on.
All right, I got it.
Returning to the theme of helpful buttons, setup is maybe the most important part of the process, because of course you can't set it up, can't do anything else. And when you set up an npod, there are a lot of choices to make. You have to pick the number of volumes you want to use, their size, how they're exported to the different nodes, how much data redundancy you want, what your snapshot schedule is, what your boot volume is. And all these decisions can be made for you through the use of templates. These are configurations that we provide based upon our experience, our knowledge, and the data we collect from the field that say, if you want to run this kind of workload and you have this number, these SPUs, from the SPUs, we know how much storage they have, what their disks look like, and based upon the workload, we can automatically configure a npod for you. Of course, users can write their own templates, they can configure manually if they want to, but in terms of getting the user up and running immediately, templates are one of the optimizations we provide.
So I guess the question,
Sure.
you know, let's say I've got 24 SSDs in a server. Do I have to allocate all 24 to the npod, or can I allocate some portion thereof?
I suppose it depends how they're hooked up. If they're all hooked up to the SPU, then they are going to end up in the npod.
But they're all connected to the server PCIe bus kind of thing, right?
Well, actually, no. So if you remember back to the diagram that I showed, the SAS connectors are coming directly from the SPU, and those are connected to the SSDs within the server. So the server itself doesn't actually see the SSDs that are plugged in, but what they see are the volumes that are presented.
What about the NVMe SSDs that are sitting in the server?
Those they would still see if they have them that are directly connected on the motherboard, absolutely. But those aren't available to our storage. Those would be used for whatever specific they want to run on the server. Good point.
I'm sorry, so those aren't available to npod storage?
It depends. It depends. If the NVMEs are connected in the mid plane, and then they are connected, the mid plane is connected to our card, then we take over those drives, and then they become a part of the npod. If they're somehow connected differently, so for instance, if you have an M.2 device that is sitting on the motherboard, and that's an NVMe M.2 device, that's not connected to our card, and it's not visible to the npod. So that's usually typically used for boot. But typically, the front connected NVMe devices that are U.2 or U.3, those will be connected to us via the mid plane, and the host doesn't see those. We see those. We have a PCI on the card itself sees those drives.
Okay, thanks.
And just to close out with an example of how the configurations can vary, we have a couple of examples here, Mongo, Kubernetes, and a couple of VMwares. So for MongoDB, Mongo does its own data replication. So, and of course, access to storage is very important. So for MongoDB, you're going to want to configure your volumes so that compute and storage are on the same node. And you're not going to want to set up any mirroring because you'd just be wasting storage and money. Kubernetes is a little different. Again, with Kubernetes, you're generally going to want to try and co-locate storage and compute. You will typically want to set up mirroring because a Kubernetes workload is varied and you can't assume it'll be doing its own mirroring and data protection. But the wrinkle with Kubernetes is you tend not to pre-allocate volumes. Volumes tend to be built on the fly by the Kubernetes administrator using a persistent volume claims and what have you. A point I would make here is that a Kubernetes administrator running a system backed by Nebulon storage doesn't need to know that it's backed by Nebulon storage. The administrator will just work through Kubernetes and the CSI driver just as if they were dealing with any other system. VMware has a convention where every volume is exported to every node. So again, you're going to set your volumes to export differently. But you may or may not want mirroring. If you're working in development, you probably wouldn't want mirroring. And if you're working in production, obviously you probably would.